start by talking about something completely unrelated, it would seem. My motivation here is going to be on maximal curves and maximal hypersurfaces. And I'll begin with a very easy question to state. So let's suppose we have C over FQ. So this is going to be a non-singular projective curve over the finite field with Q elements. And let's say the genus is G. And we're interested in the number of points of C over the extension FQ to the n, right? And by the famous Weil conjectures, we have a bound for the behavior of this number. I mean, it's roughly Q to the n plus 1. And the error term is bounded by twice the genus times the square root of Q to the power. Oh, excuse me? Well, I always hear the whole suite of things referred to as the Weil conjectures, but by now they've long been proved by Deligne. So I don't know. I just always hear them Weil conjectures. Also, you hear local Langlands conjectures a lot, but now, they're, at least in the classical, complex case, it's a theorem. So, all right. So I'll give you. So by maximal, I mean that this bound, which comes from the topology, the genus, is attained. So can you obtain the maximum? So max be obtained, and the answer is yes. And I'll just throw out a few of my favorite examples of this phenomenon. So here's the curve, and I'm going to just switch from you can see why Q should really be a square for this. So if you want to obtain this maximum, so how about this curve y to the Q minus y equals x to the Q plus 1? So the projective curve with this affine equation. And here the genus is Q times Q minus 1 divided by 2. It's some simple calculation. And this is maximal, but relative to the field FQ squared over here. So some exercise you can check. And I'll give you another example too. So let's say Q is odd, and it's just y to the Q minus y equals x squared. And so this will be maximal as well. The genus is this time just Q minus 1 over 2. But to see the maximality, it's defined over FQ. Both of them are defined over FQ. But to see the maximality, you may have to pass to some extension, maybe FQ to the fourth. It's potentially maximal. And so here we get families of curves parameterized by the Q, and that are maximal. And what's very nice about them is that they have very large automorphism groups. Hurwitz's theorem for a Riemann surface is a bound on the size of this automorphism group relative to the genus, but these violate this very flagrantly. Here, the automorphism group is a unitary group in 3 variables over FQ squared, and here it's something like PSL2 FQ. So we have these nice examples of curves with very large automorphism groups that have this property of maximality. All right, so that's the case of curves, and these things are very widely studied, by the way. I'm not so sure studied as what the generalization of this would be to higher dimension. So I'm going to say V. So maybe I shouldn't write over here because of this thing, but well, yeah, I'll just switch these two boards, and that'll be that. All right. So in higher dimension, by maximal, it should be there are the most number of points relative to the topology of the thing. So I'll make that more precise. Let's say C over FQ is a variety. And so non-singular, let's say, and we're interested again in the number of points of C over a finite extension f of Q to the n, and you can interpret this in some topological way. This is the number of fixed points of this map from C over the algebraic closure to itself. And what is that map? It's the Frobenius map. So I'll put it right here. Frobenius map, the one that takes a point and just raises all the coordinates to the qth power. And if you're fixed by that map, then those coordinates have to belong to fq to the n, except I have to raise it to the nth power. So this is the qth power Frobenius to the power of n. And so if you're counting fixed points, there should be a Lefschetz fixed point formula, and that takes the following form. It's this alternating sum of negative 1 to the I minus 1 times the trace of this nth power Frobenius map. Acting on what? It should be the ith cohomology with compact supports of C. And now to get the action of Frobenius that I want, I have to base extend up to FQ bar. And the coefficients, they have to be L-adic coefficients. So they live in some L-adic field. L is different from the characteristic of, oh, here we go, of FQ. And so whatever this thing is, it's sort of an analog for the usual compactly supported cohomology, but in the setting of objects in characteristic P. All right, so to the, what have I done? Just to the I, because yes, that's right. This one to the I, right, okay. To the I, okay. So, and so what I'm going to say by maximal is that, so we've got the Frobenius acting on these spaces, and the eigenvalues of Frobenius acting on the ith cohomology. Well, a priori, they're algebraic numbers living in the algebraic closure of this, but in fact, they're algebraic over Q as well, and you can shove them into the complex numbers, take their absolute value, and these eigenvalues have to have absolute value Q to the ni, sorry, Q to the I over 2. So, okay. And so the fact that this is true, it's the Riemann hypothesis, it corresponds to this, the Weil bound for curves that we had over here. And by maximal, I'll say C is maximal if all of the eigenvalues of Frobenius are as big as they possibly can be. All the eigenvalues will have to be equal to Q to the I over 2. Okay. So you have to make sense of this fact. I mean, Q might not be a square, in which case oh, excuse me. Yes, negative 1. I want the cancellation to work out so that all of these eigenvalues are contributing to the set of rational points. So sort of the most points possible relative to the topology. Okay. All right. So you could give examples of this. I mean, you could take the curves I gave are examples of these, and you could cross them together to get other examples. And you know, the projective space is an example, and other Grassmannians are an example. But oh, yeah, I could. I don't think anybody has any oh, my God. Just fell into an abyss. My God. All right. Yeah, there's plenty of, no lack of erasers here. Yeah, it's true. Cryptographers are very interested in the production of these maximal curves as the genus gets larger and larger. But what I'm going to do is try to produce a family where the topology does change, and you get a whole family parameterized by a Q and a dimension. And so what I'm going to say, the following is my challenge to all of you. It's such a simple problem, but I really have no idea how to solve it. So let's say n is at least 1, and I'm going to let z, I'll call it z over fq to the n. My base field has to be q to the n, be the hypersurface, and it's going to be an equation. So it's going to be one of these Artin-Schreier kinds of extensions, just like the two curve examples I gave you. But on the right side, it's this terrible determinant, and here it goes. All right, so the first row, so these variables x1 through xn, so x1 goes like this. So this is some object over fq to the n. So you could already see that these things I'm putting in the top row, they tend to vanish a lot when the variables take values in the field of q to the n elements. The last guy is 0. And then the rest of the rows are a bit simpler. Well, OK, I'll put a third thing here, so the pattern will be more obvious. But so the indices kind of move in diagonals here. And so here's xn minus 2 to the q. Here's x minus 1 to the q. Oh, what have I done? Oh, God. Wait. Oh, I'm missing a q. Thank you. And then a 0, and then a 1, and the pattern will continue over here. That's 2 to the q. And then in this subdiagonal, there's all 1s, but everything below that subdiagonal is all 0s. And so the final 2 entries are a 1, and then an x1 to the q to the n. OK. Oh, sorry, there's a q squared here. OK, I'm happy about this. All right, so should be square. So this thing is how many variables? There's n variables. The dimension is n minus 1. And and my challenge is to show that this z is maximal. And that would really be great because it would give us kind of a wellspring of hypersurfaces with lots and lots of points. And I think the topology here is very, very interesting. So if you can help me with this. What? It's non-singular as an affine hypersurface. That's easy to check. But if you try to projectivize it, it's not at all clear how to compactify. I mean, I think that's extremely hard. So if you can show that this Z is maximal, I'll buy you a case of beer or whatever your favorite thing to drink is. What? It's definitely coming. It's definitely coming. So I'll just give you it's definitely. I'm going to tie it in with the title of the talk. My hint to you, if you do want to help me solve this, is that the automorphism group of the Z is huge. It at least contains the following group. I'm going to write down some bigger matrix, but. Here it is, 2 to alpha n, and then the next thing was 0, 1, alpha 1 to the q, alpha n minus 1 to the q, and then down, 1's along the subdiagonal once again, and here's alpha 1 to the q. No, here's just 1. OK, great. And the pattern is that the alphas, all right, so this is a group. The alphas belong to fq to the n. So there's nowhere to write that. I'll write it over here or something. Fq to the n. And so this is a group. It's solvable. It's one of these nilpotent groups. And it belongs to, so that group belongs to gln plus 1 of fq to the n. And this group knows how to act on affine n space. And that group actually preserves this equation in affine n space. So there's a large automorphism group acting here, and that may be of some service if you want to help me with this challenge.
Why are you expecting it?
OK, here comes that. OK, right. So next kind of, yeah. OK. So it turns out that this hypersurface appears when you try to desingularize a certain Shimura variety. So I have to kind of lay out what this means. So I mean, we're already a bit late. So if you just give me a time, I will stop at that time. So that time is 5:10. No one ever 5:10. Perfect. OK. So I'm going to bring up something that's been referred to by many of the other number theorists here. It's the local Langlands correspondence. And I'll run through it very, very quickly. So here's, OK. So on one side of it, we have, it's a bijection between two sets. And what are the sets? On one side, it's n-dimensional representations of a certain group, a Galois group of, well, I'll say f bar over f, where f here is a local non-Archimedean field, which is either QP or FP double brackets T or some finite extension thereof. And so on one side, we want to understand the arithmetic side, representations of Galois. And on the other side, it's irreducible representations of GLNF. OK, there's many adjectives that should really go along with this. I'm not going to write them down. And these two are linked by the local Langlands correspondence. And when F is p-adic, I mean, the existence of this correspondence was proved by Harris and Taylor. And they used kind of an intermediary, which I'll call X, which is some sort of geometric object. And I won't say what it is quite yet, although it's certainly related to Shimura varieties. But the idea behind it is that it has an action by GLNF. OK. Chalk, OK. So X is a geometric object over F, and it admits an action by GLNF. And here we are, we're trying to relate the representation theory of two groups. And here's sort of in broad strokes how you might do that. Here is this geometric object X that admits this action by the group. And if I consider the cohomology of that thing, hi of X, but I have to base extend to F bar. And it's going to be a tall cohomology because I want to preserve the arithmetic character of this calculation. So now that I've base extended, the thing has an action of the Galois group. F bar over F, and an action of the GLNS. And so I've kind of linearized the problem, linearized the actions. They both act on a vector space. And very, very roughly, the idea is that, well, if I take the Euler characteristic, this is going to be the direct sum over representations of the product group rho tensor pi, where these guys are in are related by the local Langlands correspondence. So sort of in the decomposition of this big group, you get this, you kind of, it's the local Langlands correspondence is manifested in the cohomology. And so this is the idea behind what's known as non-abelian Lubin-Tate theory. It's like a generalization of local class field theory. Okay. Okay, so that's sort of how the local Langlands correspondence was proved in dimension n. Sorry for p-adic fields. And but what is this x over here? So this x is some sort of moduli space. Okay. So x is called the Lubin-Tate tower. And it's the moduli space for objects called formal OF modules. In technical terms, it's moduli of deformations of formal OF modules of height n. But maybe the right thing to do is not to give a precise definition for the x, but rather to draw an analogy with something a bit more familiar. So I'm going to erase the correspondence. So here's kind of the bad news is that x isn't even one particular thing, but rather it's a whole tower of things. So here's my analogy. So the modular curve x of 1 is a familiar object to number theorists. It's just h mod SL2z with some cusps added in to make it projective. And sitting above it is this tower of curves where x of p to the n is the upper half plane modulo this group gamma of p to the n. So this is one of these arithmetic subgroups. And this is the set of all matrices M in SL2z, which are congruent to the identity mod p to the n. Okay. And so we have this. So these things they're projective curves over Q really, and they have an action. I mean, this is normal in SL2z. So this thing has an action by SL2z mod p to the n, and so the whole tower is an action something like GL2. You can fix things so that it actually is GL2. Well, okay, this Lubin-Tate space is set up sort of similarly. So I mean, there's something which you might call x0 at the bottom, and there's x1, x2, and it goes up. But what sorts of objects are they? They're really p-adic objects. This thing on the bottom is like the unit open ball. And these things on top are étale covers of the ball. So they're not actually varieties over a number field. They're more local in nature. They're rigid analytic varieties. So it's something. What's that? Yes. It's. No. That's well. You could set it up that way. That's sort of like the Drinfeld tower. But I mean the Lubin-Tate tower, where at the bottom level of the Lubin-Tate tower, it really is an open ball. And these things are coverings of the ball. There's some other group which intervenes, a division algebra, and then when you take the quotient, then you get your upper half plane. Okay. And so this is something a bit more bizarre, but this picture does sort of kind of embed into this picture. All right. So if you take these guys and localize them at certain points, you get these guys. So there's a relation to the classical theory of Shimura varieties here. Oh, okay, well, right. So this, all right, so this local Langlands correspondence, yeah, here it is. All right, so it's, yeah, so the fact that the cohomology decomposes in this way, I mean, that theorem is just a statement about these local x's over here. But the proof of it certainly makes use of the fact of these objects over here, these global objects over here. So it's a local theorem, but currently it only emits a global proof. And so my kind of modest attempts to treat the problem entirely locally have led me down this path where I've been trying to analyze these spaces X and prove things of the following sort. So my kind of goal is to find pieces. And by pieces, the technical term is affinoid subspaces or subvarieties of X, which admit good reduction. Okay. And I'll just say a few words about this. This X thing, it lives over a field F, which you can think of as QP. You can try to find a model of it over a ring of integers, but when you do that and when you reduce mod P, there are horrid singularities. And that makes the problem of studying the cohomology very difficult, or very interesting, depending on how you want to look at it. But maybe you could find just a little piece of the thing which has good reduction, and that will make it easier for you to break off a piece of that cohomology and see that it realizes the local Langlands correspondence there. And so, yeah, all right. So I'll just say that our X thing does indeed admit an affinoid subvariety whose reduction is this variety Z of the challenge of that with that big equation that I wrote down. And well, there's more to it than that. The fact that it should be a maximal hypersurface, a maximal variety, is intimately related to this fact that X realizes the local Langlands correspondence. And so you definitely expect it to be true.
What's the reasoning then?
Okay. Yes. The reason that you would expect X to have these properties. Sure. All right, well, here's our X. X has an action by GLNF. And here's something like ours, well, okay, I mean, the affinoid itself is maybe Z tilde. And it doesn't have an action by the whole thing. It has some action by a stabilizer, which you might call K. And I can talk about the action of Galois on this thing, and I can give a precise description of the action of Galois on the reduction. And therefore, you should also be able to translate that action into an action by the local Langlands correspondence and how you think the cohomology should act. And the more precise thing I would like to say is that the cohomology of the Z with QL coefficients, together with its action of K and Galois, well, what happens with it is that when you induce from K up to GLNF, this thing should decompose into a sum of rho tensor pi's, where rho is a Galois representation, and pi is a representation of GLNF. And because we know so much about the local Langlands correspondence over here, we have to know these things. We have to kind of deduce what it has to be over here. And so that's why I strongly suspect it to be true. And then I've tested it for various values of Q and N, and it's sort of beyond a doubt it's true. But I have no idea. Thank you very much. Okay.